In the last lecture, we have compared recursion versus iteration, and we saw that in many cases, iteration performs better than recursion in terms of time and space complexity. But there are situations where recursion is preferable instead of iteration. Now let's examine the situations where we should use recursion and when we avoid it. As we discussed in our previous lectures, the recursion is always used if we can easily break a problem into similar subproblems. So in these kinds of cases, we should always use recursion. Now the next point is that we should be aware of that whenever we use recursion, it brings with itself extra overhead. As a programmer, we might not be aware of it, but the system manages it internally. So there might be time problems as well as space problems. So if you think that system will handle it without any problem, then go for recursion. This means that the recursion method that you are developing will be run on superb computers. But there might be situations we cannot compromise either with time or space. Then in those cases, we need to avoid recursion. For example, if you are developing a mobile application which should run on low memory devices as well, so in this case, recursion is not advisable. Similarly, if you are developing an algorithm for critical system which must be so fast, like the airbag system in the car, where a fraction of second matter, you must avoid using recursion in these kinds of application. So the next point here is that there might be situations when we need a quick solution. Instead of thinking efficiency of algorithm, we develop solutions using recursion. As we saw in our previous lecture, writing code using recursion is much easier. For instance, solving mathematical problems like factorial or Fibonacci, we can use recursion as an easy solution. So in the next lectures, we will see how to implement recursion methods for factorial and Fibonacci numbers. So recursion adds clarity and reduces the time needed to write and debug code. If you know your input into a function is going to be small, then recursion is certainly a good choice if you want to declutter your code. If your input is sufficiently large, however, the sacrifice of speed and memory for the sake of clarity becomes less attractive and functional. Now the next point is that recursion is very useful when we traverse a tree. It's better at tree traversal. This one is a little more advanced. An extremely simplified version of what this means is as follows. A tree is a collection of objects that are linked to one another. Imagine leaves on a tree connected by branch that are turned into connected other branch all the way to the root. Here you can see a sample tree data structure. Even though we are going to discuss this in detail in tree section, I'm just giving you a simple example here. Because recursion in a tree traversal is very efficient. One of the more efficient ways to traverse this tree when looking in a specific leaf. So we can do it by recursively following a single branch until the end of that branch, until you find the value that you are looking for. For example, in this case, if we start from here, we need to go all down till 1. So in this case, our recursion function will be very efficient. There are different types of traversal of tree, which we will discuss in tree section, but here you just need to know that recursion is very beneficial when you use pre-ordered traversal, where we recursively following a single branch until the end of the branch to find the value that we are looking for. Here we see that pre-ordered tree traversal works like this. It starts from 15, then it goes to 9, then it goes to 3, and then it goes 1. We see that this branch is finished. Then it goes to 4, then again it goes back to this side, which is 12. Then again it goes here, 23, 17, and at the end 28. We will discuss this pre-order traversal in 3 sections. Here I just want to show you that in this case recursion is very beneficial. Finally, when we use memoization inside recursion, the time complexity can be reduced. This means that if you memorize the result by saving the value of each calculation for further use in the recursive calc, you can in fact reduce the time complexity. This is also an advanced topic, and I don't want to confuse you here, so we will talk about this topic in dynamic programming section. Let's continue to see in which situations we cannot use recursion. So here we can easily say that when we face the reverse case of these cases we mentioned here, we cannot use then recursion. So if we cannot divide our problem into similar subproblems, this means that recursion cannot be used. And if time and space complexity matter for us, then recursion is not advisable. Recursion uses more memory. Because the function has to add to the stack with each recursive call and the keep values there until the call is finished. The memory allocation is greater than that of an iteration function. If we use embedded memory, for example, an application that takes more memory in phone is not efficient. And the next point is recursion can be slow. If not implemented correctly, it can be much slower than iteration. It's actually pretty difficult to write recursive function where the speed and memory will be less than that of iteration function, completing the same task. The reason that recursion is slow is that it requires the allocation of new stack frame. So that's all for this lecture. Hopefully you understand when we can use recursion and when we need to avoid it.